Here's part one of a video dealing with resistive force and terminal speed. And we're dealing with fluid resistance here. An example would be if you took your hand and placed it out of a car window when your car is moving really fast. You can feel that fluid resistance, can't you? You might stick your hand out like that, and then when the air hits it, it'll raise your hand up. If you change the angle, it'll go down. You've done that before, where you can just treat your hand like an airplane and feel the effects of that air resistance. So it does have an effect. If you're riding your bike, for example, into the wind, it's not a pleasant experience, is it? If there's no wind, you can ride much easier. If you're riding against a headwind, though, it's pretty tough to make headway. So air resistance and other types of fluid resistances are a significant factor in affecting motion. Now, fluid resistance can be at low speeds. So at low speed, fluid resistance is pretty much a linear relationship. So if this is the force of the fluid, I'll just put lowercase f. We can say it's equal to negative k times v. In other words, the resistive force is proportional to the speed. And this is some proportionality constant. We can call it the coefficient of resistance or something like that if you want. Now you could use K, you could use C, you could use D, whatever you want. And this coefficient here, it depends on the shape and the size of the object. It depends on the properties of the fluid, such as the density of air. This is the drag coefficient. Okay, so we could write it like this, or we could write it like this. Sometimes you see it where they use B, negative BV. So a lot of different ways. You could use D if you wanted to. So at low speed, such as like maybe a little styrofoam, a piece of styrofoam packing material that you're dropping through the air. It goes very slowly down. This would be an appropriate relationship there. At faster speeds, though, let's say 20 meters per second or something like that, then there's a relationship. You might have it like this, where it's the resistive force depends on the square of the speed. So as the speed doubles, the resistive force quadruples. If you triple the speed, the resistive force is 9 times bigger. If you quadruple the speed, the resistive force would be 16 times bigger. So for faster speeds, we have a squared effect. So it could be F equals negative kV, or F equals V squared, negative CV squared, or F equals negative BV squared. Alright, at faster speeds we have a squared relationship. At lower speeds we have a linear relationship. Okay. Now the problem with dealing with resistive forces is that we can't use Galileo's equations, since the acceleration is not constant. The velocity is going to change. So instead we need to start from square one using Newton's second law. So using the second law, or Newton's second law, sum of the forces equals ma. We can come to grips with the problem. And we'll have to use some calculus here. Let's say, for example, we have a pearl or something like that, or a lightweight marble, being dropped. Here's some water, and we're dropping the bead or the marble into the water, and it sinks. Okay. Let's draw a force diagram for that. So here's the little bead or pearl or whatever. Well, we have the weight, don't we? The weight of that object is mg. And then there's the resistive force due to the fluid that's pushing upward. And if this pearl or whatever is sinking, that must mean that the weight is bigger than this resistive force. Okay, so which one of these two equations here would be appropriate for something like dropping a little pearl or a bead into water and watching it sink? Be the first one, wouldn't it? So we would expect to see some kind of linear relationship. Okay, now as it continues to sink, and let's say it's a deep tank of water, as it continues to sink, what happens to the resistive force? Well, the resistive force gets bigger, doesn't it? The weight still stays the same, but the resistive force gets bigger and bigger. And if it drops far enough, the resistive force F will increase to the point where it equals the weight in magnitude. And here we see that the sum of the forces equals 0 at this point. Up here at this point, the sum of the forces was equal to ma, and the a was kind of small there. Here, the sum of the forces equaled ma, but the a was bigger, wasn't it? Because there was a bigger difference between mg and F. Here, the difference between the weight and the resistive force is less, so the acceleration would be less. And here, there's no difference between the weight mg and the resistive force F, therefore there's no acceleration. So once that bead speeds up enough, then the resistive force is equal in magnitude to the weight of that object, and it has reached what is known as terminal speed. Okay, so it's reached terminal speed once it gets to this point. Now what is F? Well, we picked this as our relationship, so I can say, okay, F was equal to what? Negative kV. This is mg, right? So if we use our little relationship, sum of the force equals 0, we have, excuse me, let me get the lights back on. We have what? We have mg, plus a negative or minus kV equals 0. Now at this point, once the resistive force is equal in magnitude to mg, then this velocity here is known as the terminal velocity, or I can just put v sub t right here. At this point, it's not going as fast, it hasn't reached terminal velocity. At this point, it's going very slowly. It's accelerating more, but the velocity is slow. So here the velocity is small, here the velocity is bigger, and here the velocity has reached maximum terminal velocity. So we end up with this relationship right here from Newton's second law, and we can rearrange it and solve for Vt. So what would Vt be equal to if we rearrange that? Vt, or terminal velocity, would be equal to mg over k. And this would be the relationship And that's how you'd find the terminal velocity for a little pearl dropping down through something like water, where we are assuming that it's a low speed situation, and we use this relationship between resistive force and speed. Okay? Now, let's look at some generalized graphs here and see what happens to the acceleration versus time for some object like this that's dropping through water, where there's a resistive force and it's varying in a linear way with speed. So let's put the acceleration over here, and we're going to compare acceleration versus time. Okay? So here's time, here's acceleration. If there was no fluid resistance, in other words, if it was dropping in a vacuum, then the acceleration would just be 9.8, wouldn't it? It would be g equals 9.8. Okay, but with increasing fluid resistance, what happens? If there is fluid resistance, then the acceleration is big at first, close to 9.8, but then it drops off fairly rapidly with time until there's no acceleration at all. Zero acceleration. Once it reaches zero acceleration, then that would mean that it's reached terminal velocity. Now let's take a look at a graph of velocity versus time. So velocity, let's say in meters per second, versus time. Okay. Well, with no resistance, what happens to the velocity? It keeps increasing at a constant rate, doesn't it? And what's the slope? 9.8. So if no resistance, then the slope is 9.8, and we're in good shape. So g equals 9.8. That's the slope of this velocity time graph. What if there is fluid resistance? Well, the object doesn't continue to accelerate at 9.8. It may start out at about 9.8, but then quickly its velocity quickly declines until it reaches an asymptote. So with fluid resistance, then we end up with that. And guess what the asymptote is? Terminal velocity. I'll put Vt there. See what I mean? I'm not sure if that's really an asymptote. I'm guessing it is, but it just seems to me that it actually reaches it. And usually an asymptote is something where it's not ever reached in real life. Let's look at a position versus time graph. So I'll put position on the y-axis. So position versus time. We know that when you're dropping an object in free fall in a vacuum, we get our typical parabola. Nice parabola. Okay, so this is no fluid resistance. But if there is fluid resistance, the curve straightens out. So it might be curvy at first, but then straightens out. So this is with fluid resistance. Can you see why that would be? Here it's fairly curvy, but then after a while it just becomes straight, which means what? If this is the straight part, what does that mean? That means the slope is constant. And what is a constant slope for a position time graph? That means the velocity is constant. So if we find the slope of this region here, that would give us terminal velocity, huh? I'll put VT, terminal velocity. Whereas with no air resistance, the slope keeps getting steeper. It might be that steep here, it might be this steep here, it's even steeper here. No terminal velocity. Okay? Thank you, everybody. That's part 1. I'm going to stop at this point and get ready to do some math.